Welcome to a new episode of Pioneers in Electronic Structure. Today it is my pleasure to have here with me Risto Nieminen. That was for many years professor in Helsinki and one of the pioneers in our field. Welcome, Risto.
Thank you.
I would like to start to go through your life, your scientific life. You were in the military in between 1966 and 67. You were a Marine in Finland. And then you started your study in physics in 1968 at the University of Helsinki.
University of Technology, yes, in Helsinki. Yeah.
These were interesting times to start at university in 1968. And you studied physics, right?
Yes, yeah.
So what are your recollections from this time? Were you a good student, an interested student?
Well, I'm sure I was a good student, but I guess you are referring to the turbulent times that were happening in Europe and elsewhere. So it was in the middle of the Vietnam War, there was a very strong student movement, a lot of activism, and that certainly was felt also on the campus. I cannot claim that I was anything particularly active in the student movement, but of course I lived in it, and those were interesting times, as you said, and the university establishment was kind of in turmoil in a way, and some of the structures and cultures were changing, some for the better, some for the worse, but I enjoyed a student life, was not particularly active politically or otherwise, but of course following what was going on. And I have very many good memories of those early days.
And was it clear already for you at this time that you wanted to follow an academic career in physics?
Yes, I think it was. I have made up my mind quite early that I wanted to try that, and already as an undergraduate tried to become involved in the research labs and research activities in the department. So I had an ambitious goal to become a scientist already at that time.
So the Helsinki University of Technology now is called Aalto University, and it must be very, very different from your times now.
Well, it's of course different. It's much bigger because of the merger with two smaller other universities. So the School of Art and Design, the School of Economics. But at the heart, Aalto is very much technical university, if you like. We're at a very strong tradition in science and technology. And what was good about the Helsinki University technology, those good things have been preserved and improved, including one of the most fantastic campuses in Europe, in my opinion. Good facilities, good community. But of course, many things have changed. A much more diverse community nowadays, both the faculty and the students, much more international, much more broadly oriented. But it's really my alma mater and the place that I really love.
So you finished your studies. You did your master thesis in 1972. We will then discuss the topic and the scientific part. But then you went for a postdoc in Cambridge.
No, I did my master's in 72, but then I wanted to kind of broaden the vision, broaden my training and education, and I got a 2-year scholarship from a private foundation to go to Cambridge, where I spent 2 years as a graduate student, and then eventually came back to Helsinki and defended my thesis in 1975. So I was a student in Cambridge, and that was a very, very important period for me, considering the connections that I made. I shared an office with Mike Finnis and made many good friends while at Cambridge and broadening my perspective. And of course, theory of condensed matter, the group that I was working in was and still is one of the top places in the world. People like Phil Anderson and Sam Edwards and many other Nobel laureates around. So it was a fantastic experience for a young kid.
Yes, I can imagine. From Cambridge, then you came back to defend your thesis, your PhD thesis in Helsinki.
Yes.
And then you moved to Denmark, to Nordita. I'm sorry, to the Nordic Institute for Theoretical Physics.
Yes.
To many of us that are not that do not know the story of Nordita, maybe could you explain what it is or what it was at that time and its importance for the physics in the Nordic countries?
Yes, the history goes back to 1950s actually, and of course it's very much around the legacy of Niels Bohr and the community of theoretical physics in Copenhagen. And I think the story goes something like this, that at that time there was a motion going on in Europe to start CERN, the big particle physics laboratory in Switzerland. And one of the early ideas was to build its theory section in Copenhagen. But that didn't really pan out. And then the Nordic community, Sweden, Finland, Norway, Denmark, they got an idea that instead of building this theory department of CERN in Copenhagen, let's build a joint Nordic Institute for Theoretical Physics around the legacy of Niels Bohr, if you like. And that's how the institute got started, and it got funding directly from the ministries of education in all those participating countries. And it was one of the first really powerful realizations of Nordic collaboration in science. There are other institutes of similar nature which were founded later. And early on, this institute was built on the idea that every year a bunch of young doctors from the Nordic countries would come to Copenhagen to work together. There was a visitors program and also connections to the local universities. And at least in Finland at that time, theoretical physics was still very weak. And it was very important for the later development for Finland to be a member of this institute and be able to send young postdocs to spend time there. And I believe so also for the other Nordic countries. And it formed a very strong Nordic community, but also because of the visitor program, it attracted a lot of prominent physicists from all around the world. And that's where I, as a postdoc, was able to make contact with lots of influential people. Many of them became lifelong friends and really made me able to kind of adapt into that community. There were then later developments. The institute still exists, but it was relocated to Stockholm some 10 years ago. It's more Sweden-focused nowadays. It still runs a visitor program. It still runs a postdoc program. But I think the Nordic aspect of it has weakened, and it attracts postdocs from all over the world. And perhaps it's more focused in research to what is happening around the Stockholm area than it was at at those times when I was there in Copenhagen.
You talked about this visitor program. Do you remember some of these visitors?
Yes. I remember many of them who became very influential figures, especially in my own field. John Wilkins from Cornell was a frequent visitor and spent quite some time in Copenhagen when I was there. And John had an enormous network of contact around the world, and he invited many visitors to give talks and spend time. Some of them stayed longer. For example, John Purdue, who became a good friend, and I was able to watch from a close distance how John and René Monnier and others worked on the early versions of what were later known as GGAs, gradient-corrected functionals for density functional theory, which then later really enabled DFT to break into the mainstream of electronic structure in both physics and chemistry communities.
And I've heard that there were some football matches going on besides science in Nordita that you participated in.
Oh yeah, so you read the small book on Nordita from those times. Yes, there's a very close-knit community of postdocs and visitors, and we had the habit of playing football after office hours in the nearby park called Fälledparken. The Niels Bohr Institute and Nordita were located right at the park, and so we would just step outside and kick around with the football. And it was an international community, people from all over the world, and sometimes those matches became
heated,
very heated, and I hate to say violent, and we really took it seriously, these matches. But of course that was all camaraderie, so very friendly, on a friendly basis, but you easily get excited over football. And then also I should mention that while in Copenhagen I took the habit of playing squash with the other postdocs and visitors, and sometimes that was also very excited activities. And I remember in particular John Hopfield, a famous physicist, also was visiting, and I used to play squash with John Hopfield, and I lost every time. So I still feel bitter about that.
So after you came back to Finland and became associate professor in Jyväskylä.
Yes.
For a few years, then you visit Cornell, and also for a couple of years, and then you come back finally to Helsinki. That became the university where you worked for the rest of your career. What are your recollections of this time, especially in your visit to Cornell? What do you still remember about it?
Yes, I remember many good things about Cornell. So yes, I was there twice. My first visit was right after, almost immediately after I had moved to Jyväskylä. John Wilkins invited me to Copenhagen. To Cornell, to Ithaca. And I there worked mainly with Neil Ashcroft on a topic that wasn't really familiar to me, but I wanted to learn about classical density functional theory, having worked a little bit already with the electronic version of it. And of course, Cornell at that time and later was also a very fantastic place, in addition to Wilkins and Ashcroft, there were people like David Mermin and Vinay Ambegawkar and Mike Fisher. So very strong in condensed matter physics and condensed matter theory. And again, I think it was very important for my future scientific life because I was able to make many good and strong connections. I returned to Cornell a little bit later, I think 86, when John Wilkins wanted to gather together a community of people to make a breakthrough in a way in electronic structure calculations. And it was inspired quite a lot by Ken Wilson, who had won the Nobel Prize for the renormalization group theory. And Ken had also become interested in electronic structure theory and wanted to do something different from DFT or the more traditional approaches. And there was a bunch of us. Priya Vashista came and many other people who had experience and background in electronic structure. And we worked there trying to find new ways of formulating the electronic structure problem. And of course, that was at the same time as things were very rapidly developing thanks to Roberto Carr and Michele Parinello, who developed the first principles MD approach. So that was a kind of a very exciting period for electronic structure theory and perhaps a kind of a landmark, not because of us, but because of the general feeling and several movement in the field that we can move forward and make it bigger, and that certainly has happened.
And that these were also the times where functions were developing in density functional theory. The GGAs that we now use were developed.
Yeah.
Was it clear? This is a question I already asked other interviewees. Was it clear at this time that DFT would become such an important theory, such an important technique in science?
I think so, yes. This is, of course, my personal opinion, but I very strongly felt that this will become important. It was already important, but it will become a much more broadly based approach to physical and chemical problems where you have to incorporate quantum mechanical phenomena much more accurately than had been done before that. So I saw it, and you mentioned the GGA type functionals, which really enabled DFT to break into the quantum chemistry community, which had taken another approach, which was not as easily scalable as DFT. And then the problem set also was widening, not only, let's say, traditional condensed matter solid state problems or quantum chemistry problems, but also people which have a much more stronger footing on material science or even bioscience. And this is where much of the activity expansion is happening and has been happening for a while. So I don't know if this was generally share this opinion, but I thought that this will become very, very big, and this is a very broad approach to lots of different types of scientific problems.
Let's go back to the beginning and let's discuss science now. So at the beginning of your career, you worked on positrons and interaction of positrons with matter. And this has been a topic that you followed for many years since then. Can you tell us how you arrived there as a student to to this topic, positrons and their use in condensed matter?
Yes, I was an undergraduate and probably was my second or third year as an undergraduate. I was recruited to work as a summer student in the low temperature lab of my university, and started working on building what are nowadays called SQUIDs, superconducting quantum devices for ultra-sensitive magnetic measurements. And I'm very proud of that period also, because I think I was involved in building the first SQUID in Finland at least, and taking some measurements with it. That activity, of course, has expanded enormously, and building those devices and building that technology has led in Aalto to major developments in ultra-sensitive magnetic field measurements, brain scanning, and so on. But I didn't follow that because another group leader in the university, one of the professors, he contacted me and asked if I would be willing to move to his group, which was working on positron annihilation as a probe for condensed matter. And I thought about it a little bit, and then I decided to make the move simply because I thought that, okay, maybe it's good for me as a young kid to learn, to get more experience in other fields. And I started working there as an undergraduate, and I was given the task of trying to work out some theoretical and computational techniques to interpret the spectra that they were taking, lifetime measurements and angular correlation, momentum density measurements that you do with positrons. It's a little bit esoteric technique, but relatively easy to set up equipment, but you need then somebody to work out what actually you are measuring.
So it's curious because you were a student doing theory in an experimental group.
Yes, exactly. Yes, yeah, and of course there was one graduate student and perhaps one or two more senior persons working in the same group, but I felt pretty lonely because I was given the task of working out theoretical methods for what was being measured, and but that turned out to be very important for my future career, because then I really got interested in electronic structure, and you need good electronic structure methods and understanding if you really want to work out analyze the experimental data. And so I started in that group, and actually was involved in my first scientific papers already as an undergraduate. But then I came to the conclusion that I have to go somewhere where I can learn more about these techniques. I cannot do it here. And that's why I applied for this scholarship to go to Cambridge to learn more about the electronic structure methods in TCM. So I finished my master thesis in Helsinki, but then immediately took off on this 2-year scholarship to Cambridge to learn more of these theoretical techniques, and then came back to Helsinki to defend my thesis later. We
will discuss defects in a moment, but before I would like to to talk about a paper of yours of 1977 that I believe is your first calculation using DFT, and it's a calculation of the interaction between two metallic surfaces as a function of the distance between them, two Gilliam slabs. Can you tell us a little bit more about it? It's 1977. There were not so many papers on DFT by then still.
Yes, that's right. I was at Nordita as a postdoc at that time, and there was a very influential paper that made a huge impact on me, and this was a paper by Norton Lang and Walter Cohn on Gilliam surfaces, who used a Gilliam model to calculate the surface energy of a metal. And an obvious idea came to me that I can do the same. They have already done it for a single slab. I'll put two slabs in contact and calculate the interaction energy, for example, as a function of distance. And this I did. And I'm very proud of that work. I did it alone. It was my idea, and also wrote the code single-handedly and use it for this purpose. So it was a nice proof for myself that I can also do these things. But it was really following in the footsteps of Norton Lang and Walter Cohn. That paper, of course, was enormously influential for the surface physics community as a whole. And my part of it was just a simple generalization of two slabs of Gilliams in contact.
Just for curiosity, was the code the real space code?
No. Sorry. Yeah, the code was real space code. Yeah, that's a good question because it's essentially a one-dimensional problem. And the original Lang-Cohn code was one-dimensional. I didn't have access to that code. So I wrote the code, but it's real space. Because it's one-dimensional, you can do it quite easily, actually.
And again, following this topic, so it's 1977. I suppose you programmed in Fortran 6.
Yeah.
And how did you learn how to program? It's not so common in these times.
That's right. I was very lucky, actually, already as an undergraduate. We had access to computers. Actually, my first language that I learned was BASIC. So there was some Hewlett-Packard machine, of course, ridiculously weak by modern standards, and I used that and learned to program in BASIC. But then moving on to more serious problems, Fortran, of course, was the language of choice. For example, in Copenhagen, we had access to IBM or Univac. I can't remember any. But anyway, Fortran was the language of choice that was being used at that time, and it was also at the time when you didn't have to punch a deck of cards and take it to the computer room. Remote terminals were becoming available, and Nordita where I was a postdoc, was one of the first places where there was a typewriter and a terminal where you could write your code in Fortran. But that of course made a huge impact on me because it was really kind of a revolutionary that you were able to do that remotely online, and you could get the printout of your results quite rapidly. Earlier, what you would have had to do is to punch a deck of cards, take it to the operator, and wait for a couple of days to get the results back. So the kind of
and then debug the code.
then debug the code, and that experience, I believe, was very important also in the sense that it really got me hooked on computational physics, that you're doing something actually by your hands also while you are doing it.
And being able to solve equations that you wouldn't be able to do in any other form, right?
Exactly, yeah.
Can you maybe tell us a little bit about the computational challenges, especially in these early days in doing this kind of calculations?
Well, of course, the resources really, if you compare modern standards, were quite rudimentary. In a way, I guess you work with what is available to you. And it seems to me that the case is that people doing my line, similar work as I have done, they always want to go to more resources and extend their size of their supercell or number of K points or whatever. So the appetite is enormous. So in the early days, what we had to do in many cases was to simplify the problem as much as was reasonable. For example, working with Jellium kind of models, which are essentially one-dimensional, and so on. And it was eventually when more computer resources became available that you could do real atomic structures, real supercells, and so on. I guess the situation to some extent is similar today, that even with the biggest supercomputers, you still have an appetite of improving your accuracy, improving your system size, and so on. So it's the amount of complexity that sets your requirements, but it's the availability of resources that actually determines what you can do. So it's a moving game, and of course yes. We couldn't dream of doing the kind of calculations that people nowadays do routinely for defects or for condensed matter systems more generally. So even with the DFT, the scaling is still such that the system sizes are not that big if you think about it.
Let me maybe just enumerate some of these works on defects. So already in 1980, you studied 3D impurities in aluminum. Then there are works on hydrogen in metals, helium in metals. Then come vacancies in silicon, in gallium arsenide, gallium nitride, hafnia, all these semiconductors with a lot of technological importance. From these works, is there some that still that you're most proud of from these early ones?
Yeah, well, I guess I'm still proud of all of that, but much of the work that we did on those days were at that time they were kind of put to us by the experimentalists that we were working with in rather close collaboration. And they had a specific question, and we tried to answer it. So I cannot claim credit of discovering important and interesting problem. I was trying to be useful, and I'm very happy if we were useful in interpreting. The experimental results can be, as I said, very complex, and you really have to be able to work out the external parameters very carefully. But then I think one of the things that I think went very well was the different types of defects in compound semiconductors, like gallium nitride, gallium arsenide, and so on. And they appear in different charge states, and they appear in different complexes, and with strong enough computational methods, you can really work out the signatures that they give to experiments accurately enough that you can really say that, okay, it's this type of a defect which is now doing this and this process possible. And some of these defect-related processes are very important for processing of semiconductors. If you want to achieve a given functionality, in many cases they are driven by the defect
Their defects,
chemistry or defect processes.
Let's continue. We're following more or less chronologically your scientific career. In the 90s, in the beginning of the 90s or at the end of the 80s, you became interested in another topic, very different, which was molecular dynamics with tight binding. I think that and tight binding is a very old technique, but at that time it was mostly used for fixed ion position, so you couldn't do dynamics.
Yeah.
And now it's a common practice. It's a very used technique with the density functional tight binding or other approaches that you can do very efficiently dynamics. Yeah. So again, how did this come about?
Well, I think I was, of course, like everybody else, was very impressed by the ideas of Roberto Carr and Michele Parinello, who married molecular dynamics and density functional theory. And wrote the famous Carr-Parinello-Fisher letter. And of course, we became immediately impressed and wanted to do something similar. I didn't have the resources and the possibility to write another Carr-Parinello code at that time. And then the idea came that maybe we can make a shortcut by marrying molecular dynamics with tight binding, and then use the same philosophy as they had used, but a much simpler description for the electronic degrees of freedom, but combining the 2 degrees of freedom, and that's what we did, and applied it to things like liquid silicon and so on. But of course, it was perhaps more, at that time, it was more of a demonstration that you can do it also this way. But of course, it's in no way a replacement for real Carr-Parinello, because you still have the tight binding parameters to work with. And you have to make some assumptions how they behave as a function of distance, for example, and so on. But I think that we proposed the idea, and I'm happy that to some extent the idea has lived. And people do similar things now, but for much more complicated systems, obviously.
Yeah, but it's still used every day. The tight binding parameterizations are perhaps a bit more complicated, but the basic idea is there. So we are in the 90s. And in 1995, you published, it's maybe not the first paper, but I think an important paper on real space techniques. And I think the paper is called Real Space Electronic Structure or something like that. Or finite differences and conjugated gradients. Then came a paper on multi-grid methods. And then eventually there was also a code coming out from your group called MICA, multi-grid package for electronic structure. And all these developments then in a way were catalyzing the codes, the real space codes that we have now, GPO or Octopus. You also organized an influential workshop, I think, that was quite influential in Helsinki on these real space methods. So what is your opinion about all this?
Yeah, that's right. Well, the positron calculations I mentioned, that they were all real space. But that's quite simple and straightforward, because for the positron degree of freedom, you have a single Schrödinger equation to solve. So no matter what the geometry is, you can do it in real space. But we wanted to see if you can extend this idea also doing electron electronic degrees of freedom in real space. I don't think we were the first ones. There had been some ideas flying around that this could be done, but nobody had really been able to make it happen. So we started looking at the possible algorithms, finite differences, conjugate gradient type, acceleration, and so on, and did some, let's say, token problems or model problems. No really serious application beyond the simple one-dimensional, or in some cases two-dimensional cases. But I was very happy at that time that some other people like yourself had also become interested in the same kind of approaches, and the octopus community had started work in this in Spain and so on.
And then JIPO in Denmark.
Exactly. Then it really, in a way, culminated into JIPO, which has been a highly successful electronic structure code and very widely used these days. From my point of view, I think the honest answer is that we really didn't have the resources to start big-scale development of real space codes that could be applied in realistic atomic type problems. So we were mainly relegated to working with Jellium-type approaches for different questions. So low-dimensional, one- or two-dimensional cases, which we could easily solve with our resources, but we're not pushing it into real atomic geometries in 3 dimensions. But then came JIPO, and we didn't have to do it.
If my memory is correct, you even had some experimental code using finite elements for, and you did C60, all electron C60, right? If I remember well.
Yes, we had experiments on finite elements, which was also an obvious thought for many people, and we did some excruciating experiments with that, but decided not to push it forward. Again, I think the idea of using finite elements was around at that time, and some groups tried to push it, but I don't think I'm not aware that it has really been successful.
Oh, it came back in chemistry mainly, so because you can do all electron calculations very accurately without basis sets. So now there are a few, especially in quantum chemistry.
That's right, but I think even in those cases, it's they tend to be kind of dimers or essentially two-dimensional problems. I'm not anymore very familiar with the latest developments, but to me, if I may put it this way, I think the finite element approach has been always very promising, but I haven't seen the promises realized.
So you came from Cornell to Helsinki. You've been a professor until now. I just in this period, I just would like to ask you. You were also dean from 2013 to 2016, I think. And how was it, the experience of stopping a professor teaching and doing research to becoming a dean? That is a whole different story.
It's a whole different story, and luckily I can say it happened towards the end of my career. So the last 4 years before retirement, I served the dean of the School of Science for Aalto University. And I have to say that I felt an obligation to do that when the rector asked me I felt that I can perhaps give something back to the community and help in developing Aalto University to become even better than it was. So I don't think it was an easy decision, because in practice, of course, it meant that I had to give up most of the science myself. I did have students and postdocs that I could talk to, but my own contributions were dying out during that period. But in a way, I'm happy that I did it, and I feel good that perhaps I was able to give something back and develop the university. And I'm very proud of the university. I think it's doing excellent work now and expanding nicely.
So besides all your scientific achievements, you have been involved in many initiatives, supercomputers, Psi-k, and many other things that were extremely important and are still extremely important. Let's start maybe with supercomputer. You were one of the founders of the Finnish Supercomputing Center, the CSC.
Yeah.
Can you tell us a little bit about it, its history and its importance, and your involvement in it?
Yes, when I came back from Cornell, this was 88 or so. There had been an initiative in Finland among the scientific community to obtain a high-performance computer, a supercomputer for scientific purposes. And I was involved in that movement. And then it started gaining traction. We were able to convince politicians that this could be a good idea. There had been much earlier in Finland, there had been a kind of a supercomputer at that time in Finland, a UNIVAC, which I actually used for my master degree and early career. But then there was a dry period and very little access to high-performance computing. In 88, things started to change, and a small organization was founded, which later became known as CSC, Center for Scientific Computing. And I was asked, because I had been vocal in promoting the idea, I was asked to become the scientific director of this organization. And I felt my duty is to do it, so I took leave from my job in the university, and for a couple of years worked full-time in building this center, the CSC as it's called nowadays. And we got our first Cray machines and another Cray machine, and gradually it started building. And I'm very, very proud of this effort, because we were also able to secure funding for this purpose on a long-term basis. The center has grown. It has, several hundred people now working on. We also were able to convince authorities to build a decent network in Finland and gain access to high-performance computing elsewhere and so on. And now, of course, the culmination of this is the LUMI supercomputer, number 3 in the world, which is hosted in Finland by CSC, which is a European effort. Of course, my involvement with LUMI is non-existent. I still follow what is going on, but I feel enormous pride that perhaps in some way I was able in the beginning to get this ball rolling and make the center and contribute to its success. So I'm very, very happy of this. I was asked to stay as a director of this center. And it was a struggle for me for some time. it would have been tempting to stay there, but then I decided, okay, I want to be a scientist, and I went back to the university. But I have kept my contacts. I know the people, and I'm very, very happy of what has happened. I should mention also that CSC now is very active in quantum computing also, and Finland more generally. So somehow I see this logical evolution starting from the early days when we built the center.
And another very important institution, I think we can call it like that we have now is Psi-k. And you were also involved in Psi-k essentially from the beginning. You are a member since '94, and you were the chairman for 6 years, I think. And so you were a big part of its history. Can you tell us a little bit more about the ideas at the beginning of Psi-k and how it evolved?
Yes, I'm happy to do that. I think it started in the early 1990s. People started discussing the possibility of improving European contacts and collaborations in the electronic structure area. And I think the roots of this organization really go into, first of all, to Cambridge, where Volker Heine and then also Daresbury, Walter Temmerman,
yes.
They were influential and very active in expanding from what they had a kind of a UK-wide consortium to more European level. And especially Volker had very great ideas on how to build this family of electronic structure people across Europe. And then I don't remember exact year, but probably 1993 or 4, a new funding instrument became available from the European Commission called Human Capital and Mobility. And then we decided to write the first proposals to European Commission for supporting Europe-wide collaboration, a network type operation. And that was quite successful. I think it was maybe renewed once or twice. We also had in the early 90s, we had funding from the European Science Foundation, which funded workshops in electronic structure, at least 2 or 3 or 4 of them, topical workshops in electronic structure. And then already the kind of the seeds of the community, the foundations had already been laid, and then it was decided to formalize it to what became known as the Psi-k network, and had one more successful period of funding until we were told by the European Commission that's it, now you have to live on your own. And that was, of course, a critical moment. What would happen in the future? But then I believe we made a great decision to organize it on our own, make a charity type organization rooted in UK, but gaining support from the participating Europe. Groups and countries. And then this became the Psi-k network, which still exists.
And it still thrives.
And of course, one of the sort of flagship activities are these big Psi-k conferences. Every 4 or 5 years, we had 2 of them in Germany, Schwäbisch Gmünd, one in Berlin, one in San Sebastian, one in Lausanne. So that's really a great story and a very strong and influential network. And I think one thing that I want to mention is that early on, from early on, very wisely in this network, there was an emphasis on code development, developing codes together and exchanging information and skills in codes. And that has really been the glue in many ways that has kept the community alive. So even apart from these flagship events, you have these topical workshops, but then you have also the code-specific workshops, which are very, very important, in my opinion. So I think it's a story that Europeans should be very proud of, because I know our American friends are very envious of what has happened in Europe because of Psi-k. And so I was very, very lucky to be involved in Psi-k from early on. I went to these first ever meetings and then was a chairman for some time. And now it's in good hands, of course, in the UK. So in a way, it's back to its roots. But who knows what will happen in the future.
There's another thing I would like to ask you. You have also been in the selection committee and also the chairman of the Millennium Prize. That is a prize given by Finland, maybe not as known as the Nobel Prize, but also very important. Can you explain a little bit what the prize is and your experience in being in the committee and the chairman?
Yes, the prize was set up more than 20 years ago. At that time, there was a very strong feeling in Finland that technological innovation, perhaps because of Nokia's success or whatever, deserves more visibility also within the scientific community and also within the political community and the public at large. And the idea came about that we should build tradition along the lines of the Nobel Foundation, so something similar, build a foundation that would recognize achievements in technology rather than basic science. Let's say science-based technological innovations should be highlighted and given global recognition. So this was the idea, and the foundation is still there, and Millennium Prizes are given out every 2 or 3 years. And the basic idea has not changed that much. The idea of the Millennium Prize is to recognize innovators who have made important discoveries, but at a later stage of their development than the basic science discovery that Nobel Prizes recognize. So that you can already see some kind of a scalability of these ideas into working technology, and also, which is very important, that the technology is for the good of the mankind and the planet. So the benefits of the technology have to be kind of viable and visible.
Yes, for curiosity, some of the winners were Michael Grätzel, Linus Torvalds from Linux, Stuart Parking from the magnetic. So clearly, very people who had, as you said, gave very important contributions to the science-based technology.
Exactly. Yes. Yeah.
Finally, maybe as our last topic. You were very active in scientific journals. You started 2 journals, Computational Material Science and more recently the journal called Electronic Structure. And I would like to ask you, we all know that things changed a lot since the 70s in terms of journals and publications. And I would like to ask you, what is your general opinion of what's happening now on the publication panorama, let's say, with millions of journals and H indices and impact factors, and how did this change, and is it good or bad? That's
okay. No, not an easy question, and it seems to me that scientific publishing has been a kind of in turmoil for quite some time, and it's a very diverse field. Obviously, there are different players. There are commercial players who are there in the publishing industry just to make viable business. And then there are publishers who are backed by a scientific organization and who are perhaps not so much taking profit from it, but trying to support the community. And of course, communications technology has totally changed, and we have new ways of disseminating information also in the science area. So the original purpose of scientific journals was to disseminate information, the newest developments of science as widely as possible. But the roles have changed over the years, and with the invention of citation indices and impact factors and so on, it has developed for itself another role where you try to kind of evaluate and measure especially young scientists' careers and capabilities and promise. And that in many cases has become a kind of a driving force for the decisions that people make about career moves. So it's a little bit confusing situation that what are we actually trying to achieve with scientific publishing. We of course need it, and in my opinion, it should be open, and we should use it for the benefit of everybody, for the good of mankind. But with these commercial pressures and then the career pressures and all this seem to create a little bit contradictory goals and ambitions. So I don't know how it eventually will pan out, but I think, in my opinion, the kind of a best framework for scientific publishing are these scientific societies like Institute of Physics or American Physical Society and so on. So they are in a way community controlled and community owned, and so I feel a kind of empathy towards their efforts. But then there are very strong commercial operators like Elsevier or Springer or whatever, who also are doing a decent job in many ways, publish good stuff and have a decent editorial and reviewing systems and so on. And how to match all these together and how to match the requirement or the wish for open access together, it still remains a puzzle to me. I don't see any clear one way forward out of the situation. But what I think is very important is that the scientific community should have better control of the publishing industry also. Because we produce the stuff and we take care of the editoring and we take care of the reviewing. So in a way, it's very important that we have control, and that can perhaps be best realized through the scientific societies.
Very well. Well, we have reached the end of our interview. Thank you very much, Risto. It was a pleasure.